Yes, it's the physics video lecture. Physics 105B, video lecture 34. We're going to move on, into Hamiltonian mechanics, but I'm going to formulate, while I'm still thinking about it, one more homework problem on the stability analysis. An easy one, but it should be good for you guys. So let's get that up here right away. So what we're going to look at is the physical pendulum. And we've done the physical pendulum, so I'll just go ahead and write this here. Once you analyze this, you have x second derivative equals minus omega naught squared sine of x, comma, where x is just the angle. Okay, so the angle theta again. So what we want to do is the stability analysis on this thing. And it'll be good because we have the full visualization of what's going on. The thing about this pendulum, being a physical pendulum, is that it can go through the full 360 degrees. In other words, x is not bounded here. Okay. Yeah. So for that reason, we know that it has a stable. So we know stable at x equals 0, and of course if it's standing on its head, unstable, writing down here, unstable at x equals pi. Okay, and we're just going to do this formally. So what we do is express as x1, x2 equals f of x1, x2. Right, so we want to express it in this form and then linearize about each of these two respective equilibrium points, right? This is an unstable equilibrium if the pendulum is standing up here, and of course it's a stable equilibrium down there. So you're just going to do the formal analysis, and of course you're going to find that unstable and stable. So, right, so x1 and x2, x1 is x, x2 is x dot, and so express as this, and analyze at or around x equals 0, x equals pi. And of course that analysis is the linearization, and in each case you've got a 2 by 2 matrix. Okay. Eigenvalues of the 2 by 2 matrices, respective ones for x equals 0 and x equals pi, and of course the corresponding stability, instability, etc. Okay, that's a simple enough problem, but it's perfect application. It's basically what I did with the damped oscillator, except around the two equilibrium points. Good. So having said that, our next major topic is Hamiltonian mechanics. This is something we have to know about, want to know about. I'll do it now. We have some other topics I'd like to cover, but by doing this now, we'll make sure we do an adequate job on this, and then whatever time we have left, we can do, you know, our numerous projects. So good. Hamiltonian mechanics builds out of Lagrangian mechanics. We have to already know Lagrangian mechanics to move on to Hamiltonian mechanics. It's an extension, so to speak. And so I have to, first of all, talk about Lagrangian again. And Lagrangian mechanics, you know, we had this variational principle, which I could express like this. T1 to T2, I don't need a prime here. So we had a variational principle where the Lagrangian is the difference between the kinetic and potential energies, and these Q's are the generalized coordinates. Okay. So L is T minus U. Q is the set of generalized coordinates. Generalized coordinates. Okay. And then of course Q dot is their first derivatives, generalized velocities. So we've got a whole formalism going on here. And I'll go ahead and write down the Euler. You know, I'm actually going to write down everything because we're going to need it. Have it on the upper board. So yeah, generalized coordinates, Q dot, or the generalized velocities. Generalized velocities. The equations of motion that follow from this are, as we recall, Qi dot dl dqi equals 0, 1 to n, right? So we have n equations, and these are second order differential equations. When you take your derivatives, you're ending up with a second order differential equation. So we have n second order differential equations. N second order differential equations. The space of these coordinates here, these Q1 to Qn, is called the configuration space. So the configuration space is called, I'll just put it in here in quotes for the definition, configuration space. Let's see what this configuration space. Good. So we have this, and we have one more important quantity that's going to be crucial, namely the energy. So we had, in addition to the differential equations, we had one more relation about the energy. Okay. So energy dl dqi dot, qi dot minus L, this is outside of the sum. And of course we have the very important point about this expression dl dqi dot, that was the generalized momentum. And P sub I dl dqi dot generalized momentum. Okay, so it's all coming back to you, right? That was our whole system. Now what we're going to do is find a mechanics in which the generalized momentum is one of the dynamic variables. So this is Lagrangian mechanics. When we're doing Hamiltonian mechanics, it's building on this here. So Hamiltonian mechanics, we're going to look for something called the Hamiltonian. That's a function of the generalized coordinates as we have in Lagrangian mechanics, but also a function of these generalized momenta in such a way that these generalized momenta are also dynamical variables. Okay. Now, what's that going to do? It's going to turn our system of n second-order differential equations into a system of 2 times n first-order differential equations with 2n first-order differential equations. So say we're talking about a particular mechanical system, same system up here and down here. So building on this, we want to transform our Lagrangian into a Hamiltonian in which the generalized momenta, or the momenta that were before were generalized momenta, are now also dynamical variables equally with the generalized coordinates. So the method of doing that is to take this thing here and use it to make what's called a Legendre transformation. Something that's also done a lot in thermodynamics. And I'm already going to label it H, okay? So we're going to call this H equals sum over, right, this is the piece of I, so piece of I, q sub I dot, I equals 1 to n minus L Q dot and T. Now this is actually not yet the Hamiltonian. I could write the E there. What we have to do is transform this expression into a function of just Q and P. And having done that, it's nice that they're right above each other. Having done that, then what are the corresponding equations of motion? So I'll put that here as well. We must express, here I'll number these star and double star. Express equation double star in the form of equation single star, which means we have to get rid of everything with a Q dot in it and express it in terms of P, okay? And you can say we've already done it here, but we have to do it in what remains of the Lagrangian. So we must express such as this form, then obtain the new dynamical equations. So that's our task. Okay. And everything's on the board that we need. Of course, I got to erase some of it. But we can do that. And this is where we're headed. You know, we're headed with an object like this, 2n first order differential equations, and we'll see then what we gain from that and what we don't gain. But in order to do that, we just take the complete, or the differential of both of these, total differential of both of these expressions. And we'll do them right on top of each other, and we'll have a good comparison. So let's look at this. So we'll just write here differentiate, or differentials. So for double star, we have dH is going to be equal to sum over p sub I dq sub I dot, and then plus sum over d p sub I q sub I dot, again I equals 1 to n, and then here minus the sum over dl dq sub I dq sub I for the first n coordinates there, and then minus sum over dl dq sub I dot dq sub I dot, and then outside the summations minus partial L with respect to time times dt, okay? That's the total differential of this, and now we'll just do the total differential of what we're looking for. So for this one, you know, if I leave a little space, I may be able to write in between the two lines. Here we have dH equals, we have a sum for the first n q's, so sum over dH dqi dqi, and then we have the same thing for sum over dH pi, and then outside of the sums we have, time in there as well. So outside of the sums we have plus dH dt partial dt. So we're going to just compare these two, and we have so before we do that, we have these qi dots that are missing down here. But what we'll see, we'll circle them, is that pi is dl dqi dot. So these two sums cancel against each other. P sub I is dl dq sub I dot. Okay, and now we can compare these two. Two right here. So we're just going to compare coefficients. So dqi, dqi. I have to do one more step here. That's why I wanted to leave a little room here. So let's see what we have here. This is actually minus the sum. Using the Euler-Lagrange equation, this is d dt dl dqi dot. Okay, so d dt dl dqi dot equals dl dqi. Of course, that's one way to write it, okay? So this thing here is the time derivative of this, which is, of course, pi dot. Pi dot. So we have minus sum of pi dot dqi. Okay. And now we can compare. So from these two here, so we find this dh dqi from here is equal to pi dot actually is equal to minus pi dot. Got a minus sign in there. Okay, so that takes care of those. And what else is there? These two circled ones. Qi dot is equal to dh dpi. So dh dpi is equal to qi dot. So I'm just matching coefficients now. I had to make that important switch there. Those are two canceled. And finally, the dh dt is equal to minus dl dt. So dh dt equals minus dl dt. Good. Having found these things, go ahead and showcase them. So what we have is this relation, this relation, this relation. And what that's going to mean is if these relations hold, or these relations hold when the Euler-Lagrange equations hold, and vice versa. Okay, that's by construction. And these new relations are called Hamilton's equations. So what we have now is a process. It's pretty much all on the board. You start with your whole Lagrangian setup. And then you do this construction. You go from here to here. Okay. And if you get it in the form of h just as a function of q's and p's and t, then these are your equations of motion. So that we've done. We've derived these equations of motion once and for all. I will go ahead and summarize this on one board, and then we'll start working with it. Good. Okay, so here is our procedure. Okay, so to get, I'm just going to write Hamilton Mechanics again. So you have to have done everything you have to do to get a Lagrangian. Okay, so you have to construct your Lagrangian Q1 to Qn. Jump again on that. Q1 dot to Qn dot and t. Okay. So you have to have your Lagrangian. Then I'm going to write in the following form. Then you take your, and here I'll write P sub I is dl qi dot. Then you do this construction. Pi qi dot minus L q dot of t, which is not yet the Hamiltonian, but you have to turn that expression into just the function of Q and P and T. And that can either be fairly easy or, depending on how these things are mixed up together, could be more or less difficult. The ones we do are always going to be pretty basic, so nothing to worry about there. So once you have that, then your new equations of motion, Hamilton's equations, are, so yeah, you have this Hamiltonian here, and I'll go ahead and write Hamilton's equations right under here. So you have Qi dot is equal to, make sure I wrote them down right, yeah, it's equal to dH dPi. Pi dot is equal to minus dH dQi. And this last relation here tells us something about the Hamiltonian minus dL dt. It's not really part of the equations per se, or at least by that I mean these are the ones you're then setting up and solving for. These are your 2n first order differential equations. This here is interesting. It plays a role in more advanced theories. Also, it's telling us that the same criterion for the Hamiltonian holds true for the Lagrangian. Remember, when the Lagrangian is not explicitly a function of time, the energy is conserved. And since the Hamiltonian came from the energy and is the energy, we see also if the energy is not explicitly a function of time, then the energy is conserved as well. So that much we see here already. Good. So there's our system of equations. They're also referred to as the canonical equations. Hamilton's equations are the canonical equations because they just look so good. They're authoritative. They've been agreed on, apparently. So I'm going to do a really basic example of this just to show you what's going on, and then we'll talk about a few more general features of the theory. Let's see how we're doing time-wise here. Fine. Okay, so first an example, and then a few general facts about the system. So our example is just going to be 1 degree of freedom, simple particle. Particle 1 degree of freedom. So yeah, suppose we have L equals 1/2 m. Should I call it X or should I call it Q? We'll call it Q. M Q dot squared minus U of Q. So there's our Lagrangian. And of course the Euler-Lagrange equations are just Newton's law. And the energy is dL dQ dot times Q dot minus L. There's only 1 degree of freedom. So that's M Q dot times Q dot minus 1/2 and Q dot squared minus negative, which is plus U of Q. Of course, we could have just written that down anyway. T plus U is E. So it's 1/2 M Q dot squared plus U of Q. So that's our energy. I'll go ahead and write it right here. 1/2 M So yeah, that's what you do. This is the long route. Could be more complicated, but this one is very simple. Yeah, so next, what are our equations? Okay, this is trivially true because there's no time dependence. Q dot dH dPi, so that Q dot is equal to dH dP, and right underneath I'll go ahead and write what that is. Oh, got ahead of myself. Okay. This was the energy, but we're not done yet. Okay. So now we need the Hamiltonian. Man. So now P is equal to dL dQ dot, and that is mQ dot. And right under here, this is fine, H is equal to 1/2 m, and now I have to have that Q dot squared. And I found Q dot in terms of P, so it's P over m, the quantity squared plus U of Q. Okay, so now I've obtained my Hamiltonian, and I'll just H of Q and P equals P squared over 2m plus U of Q. Okay. Boom. Good, so there's the Hamiltonian. And we're going to get its equations of motion now, Q dot dH dP, and of course that's simply going to give us back what we have right here. Q dot equals dH dP, and what is that? Q dot is equal to P over M. Of course, we just plugged it in there, we get it right back. Okay, Q dot is P over M. P dot is equal to minus dH dQ, and that means that P dot is equal to minus du dQ. Okay, so these equations that I'm going to outline are our two canonical equations. And I'm going to use this section of board since it's right here for us. So in this form, we will discuss later what's significant about it. Right now, we're just doing a consistency check. So there's two things. First of all, P dot equals minus du dq, that's just Newton's law, right? The derivative of the momentum, that's ma, derivative of the momentum, is equal to minus the gradient of the potential. So this way, if you see this here, you recognize the minus sign belongs to the Newton's law version. You know, if you're having trouble memorizing which one gets the minus sign, just see this as mass times acceleration or derivative of momentum. That's what that is in other cases, right there. So this is to remind you of that. And the final thing is we're just going to plug this P in here and take the derivative. You'll see P dot is mQ dot. P is m times Q dot. P dot is mQ double dot. So what we get here is mQ second derivative minus du dq. Okay, so that's just Newton's law. And of course, you could say we're back where we started. We didn't have to construct a Hamiltonian to do this. But just to show you that you're getting back your original differential equation, as of course has to be the case. Okay. So yeah, we're going to do a few exercises with this, get some Hamiltonians of a couple of different Lagrangians. And we'll also then learn, what the utility of this method is. It has profound applications. And part of that has to do with the fact that you have these first-order differential equations. The first-order nature of the differential equation allows us to interpret the Hamilton's equations as a vector field. Okay. So let's see. I think I'm just going to leave it at that for today. Good place to stop. Not quite. Let's do a little bit more. Okay. Now that we see the significance of this, or not significant, now we see how it works. Let's go ahead and do another couple things. I'm going to go ahead and leave that up there since it's our system that we're working with. And I'll erase these here. Okay, so now I have to do a couple of things. Let's do, so next we're just going to take the time derivative of dH dt, or the time derivative of h. Okay, time derivative of h. This is what we're talking about right here. So we'll just come out with chain rule, partial h qi dot plus sum over partial h pi, no dot here, sorry, pi dot plus dH dt outside of the sums. And here the canonical equations are going to tell us the qi dot is dH dpi, the pi dot is minus dH dqi, so these go away. Okay, these add up to 0. Just using the canonical equations, make sure you draw attention to that. Okay, right here, you plug those in, it identically goes away. And what you see then is explicitly what we had mentioned before, but explicitly proven now. Complete time derivative of the Hamiltonian is equal to the partial, explicit partial derivative with respect to time of the Hamiltonian. And that is telling us that if the Hamiltonian does not, without recourse to the Lagrangian expression, if the Hamiltonian does not explicitly depend on time, then it is conserved. Okay, so if h is not explicitly a function of time, then h is conserved. Good, so that's one important point. I think we'll add to this. So one more example, and I'll assign this one. So homework problem. Construct h of r phi r dot phi dot. Oh, my bad. H r and phi p sub r p sub phi for the central force problem. And of course, the central force problem, we know it's Lagrangian. L is equal to L of R phi R dot B dot. is that? That's 1/2 m r dot squared r squared v dot squared minus u of r. So yeah, you construct this Hamiltonian for this, and if you look at the energy that we did all of our work with when we were doing the central force problem, you'll see some very close similarities. Okay. So good. That's basic. That's a good one. Half m u r. And you know, I'll just add here. I'll just put a question here. Cyclic coordinate. That's what we're going to do next. Coordinates, question mark. We know we have one here. We're also going to have one here, and that'll be our next topic. What do we do with cyclic coordinates in the Hamiltonian system? Okay, now we'll end it with that and see you guys next time.